Hi and welcome to Unit 4, Topic 3, Video 4. We're going to look at the Hungarian algorithm a little bit further. But first let me define what this table is. This is called a costings matrix. Now you've seen matrices before in Unit 2. And so this is just basically a set of cells that represent some data. Now in this case I'm going to say there's 3 jobs and Hannah, Chelsea and Rebecca are capable of doing those 3 jobs, and this is the time it's going to take in minutes for them to complete those jobs. Now it's called a costings matrix, but that doesn't mean it has to do with cost. Typically with the Hungarian algorithm, which you'll see later on, it's going to have to do with cost or time or maybe distance. And in all cases, we're trying to minimize those allocations. Now in a later video, we'll talk about a problem where you maximize, but then you end up using the Hungarian algorithm to minimize anyway. We'll worry about that later. But for now, Hannah, Chelsea and Rebecca can do these jobs, and we want to minimize the amount of time it takes to do these jobs. So I've got the times in here. The one thing I could do is I could go through and just do it logically. Because actually when you break this one down logically, you go, let's look for the smallest amount of time. If I got Rebecca to do this job, well that's only 7 minutes, so that's pretty good. And that's probably going to be in there. It might not though, so be careful. But then if I get Chelsea to do this job, that's the shortest job for her. It's also the shortest time for job 2. Well, that's good. And then that leaves Hannah to do job 3. And I can see that in terms of job 3, 16 minutes is the shortest as well. I'm pretty sure that's the minimum time. But I haven't shown this mathematically. It's just a logical solution. And this is perfectly fine. But is it perfect? What happens if I've got 5 people on 5 jobs? Or 10 people on 10 jobs? I need a better way. I need a more mathematical way. In fact, it's really good if I have an algorithm, because an algorithm I can feed into a computer. So I'm going to show you an algorithm right now, a way we can guarantee we get this right if we just follow this set of rules, and you'll just need to know how to use the set of rules. It'd be nice if you understood where the set of rules came from. So the set of rules, the algorithm, it's going to pop up on your screen now, and I'll come in and I'll talk about it. Okay. So here's the Hungarian algorithm process, and I'll stand to the side as I'm wearing a white shirt. Step 1, we do a row reduction, which in the next example I'll show you how to operate a row reduction. And a row reduction is just to go into every row, find the minimum value, subtract it from all the values. And then we do a column reduction. Irrespective of what's happened with the row reduction, we go into every column and we subtract the minimum value from every single value in that column. Then step 3, we ask ourselves, can we cover the zeros in less than n lines? Now n is the number of items, the number of objects. So in our example I just had up on the board here, n was 3. There are 3 people involved. N will be 3 or 4, probably maybe 5. So can we use less than 3 lines to cover all the zeros? Now if the answer is no, if we have to use 3 lines, well then we're done. Sketch up a bipartite graph and find your matching allocation. But if the answer is yes, then what we need to do is we draw those lines on there. In this case there'll be 2 because we've only got 3 options. We draw the 2 lines on there, circle the minimum uncovered value, and then we do 3 things. We add it to all the double covered items, we subtract it from the uncovered items, and then we do nothing to the single covered items. Then we go back to step 3 and we ask ourselves again, can we cover all the O's in this new matrix in less than n lines? And if the answer is yes again, we cycle again. Now this cycle rarely takes more than 2 times. In a hard question it's 2 cycles, maybe 3, I don't know. Down here though, once we get to the no, once the answer is no, we're finished, bipartite graph, solved the problem. So I'm going to go back now, we'll solve that last question and then we'll do a couple more examples. Okay, well I hope that algorithm made sense. Let's apply the algorithm to this particular problem, shall we? And see how we go. And what I'm going to do is I'm going to break out of this formatting and I'm going to go into something a little bit easier. So, this particular problem I'm going to label, and really if you've got the space you really should, HCR 1, 2, 3. And the first step was to do a row reduction. So we look at each row, we find the minimum value in that row and we reduce every element in that row by that minimum value. So in this case, for Hannah's row, 8 is the minimum value. So if I subtract 8 from 8 I get 0. I subtract 8 from 11 and I get 3. And I subtract 8 from 16 and I get 8. And then Chelsea's minimum value is 8. So I subtract 8 from 9 to get 1. 8 from 8 to get 0. and then 8 from 19, which gives me 11. And Rebecca's minimum value is 7, 7 from 7 is 0, 7 from 10 is 3, and 7 from 17 is 10. So there's my row reduction, and this is step 1. And then I've got step 2. Step 2 is, again, I'll build my table, 1, 2, 3, might just put a little line there. I'm very conscious of space, HCR. Now I'm going to do a column reduction. Minimum value in each column, and reduce it. Now, what I need to note here is I've got some zeros popping up, and you might have zeros from the start. Whenever there's a zero, it means that just nothing changes. My minimum value is 0, subtract 0 from everything, I get the same thing. That can speed up the process a bit. There's a 0 there, so this is going to stay the same as well. So no 0 here though, minimum value is 8. I subtract 8 away. That gives me 0, 11 minus 8 is 3, 10 minus 8 is 2, and I'm left with this. Now I'm looking to see what matchings can I do, how many lines do I need to cover it up. And I want to minimise this as well, so I've got to be a bit logical about this. This is the one logical step. So I'll look at this, I can't get rid of 3 in one go without going diagonal, which I'm not allowed to do, but I can get rid of 2. Can I get rid of the other 2 now? No. I can get rid of 2 there, but I still can't get rid of the other 2. So actually, I've done it. I don't have to worry about going back and doing those second steps, but we'll get to those in a later example. So now I can build a bipartite graph for this information. So I've got all my matchings, and the bipartite graph comes from where the zeros are located. A 0 indicates that there is a matching between Hannah and 1, which could potentially provide a minimum value. So I'm going to start by listing out my Hannah, Chelsea and Rebecca, and then 1, 2 and 3 for my jobs. Hannah is associated to 1 and 3. 1 and 3. Chelsea is associated to job 2. And Rebecca is associated to job 1. So now I can build my minimum allocation. My matching allocation will give me a minimum amount of time required. So I can see here that Chelsea has to be matched to 2. It's the only option for Chelsea, it's the only option for 2. Now, 1 has 2 options, but Rebecca only has 1 option. She has to be in 1, and it leaves Hannah with job 3. So there's my jobs and there's my people, and that's my allocation. I go back here and I can see that matches what we always thought, and it gives us a minimum time required. So here we got minimum is now equal to 7 plus 8 plus 16, which of course is 31 minutes total of allocated time. But of course, if they can run concurrently, things are different, so you might have to enter the question based on the context. Well, thanks for joining me. I hope you've enjoyed our adventure into the Hungarian algorithm. All the best.